Okay, Assalamualaikum warahmatullahi wabarakatuh. Today our group gonna present post-quantum cryptography. Okay, our group is mostly by Ahmad Khilfi bin Zaini, Mohamat Faris bin Mazlan, Mohamat Nasri bin Karudin, that's me, and Mohammad Naim bin Abdul Malek. So we're gonna start our presentation by introduction by Naim, quantum mechanics in computation by Khilfi, will a quantum computer break encryption by Naim, why quantum computing require quantum cryptography by Nasri. Then the main project is post-quantum cryptography by Faris and conclusion by Faris. Then next I will pass to Naim.
Okay, Assalamualaikum. My name is Naim. For introduction part, we are introducing two general meaning of quantum computing. First, quantum computing is a machine use the properties of quantum physics to store data and performing quantum computation. Okay, the second is post-quantum cryptography. Is the development of cryptography algorithm that is invisible, power, and applicable against the classical computer and quantum computer. And NIST NIST claim that quantum computing already break a public key that used for RSA and etc. Next.
Okay, before we go forward, let us explain a little bit about how quantum computer became a quantum computer. So because of quantum computer, they use the concept of quantum mechanics in computation. Quantum mechanics such as superposition, entanglement, and quantum tunneling is very fundamental that need to be used in computation for quantum computer. So that is a simple definition for superposition. That is two-state of matter can exist at a single point of time. Entanglement is where two matters are entangled even at a galactic distance. And quantum tunneling, the ability of a matter to phase through a potential barrier. Do note that this elemental of quantum mechanics is just a few that many that exist in quantum physics. Next slide. So first is superposition. So what is superposition? A superposition is a matter can have two states at the same time, also known as Schrodinger's cat paradox. We also learn about superposition in physics, especially in high school where we learn about double slit experiment. So because of superposition where an atom or a matter can have two states, we use quantum tunneling. Why quantum tunneling? If we learn about the Moore's law, where the transistor of a chip is so small, where an electron can quantum tunnel through a potential barrier. That is quantum tunneling, where a matter can phase through a quantum barrier. So they use probability of wave function, mumbo jumbo wording about quantum physics, and also because of they use superposition instead of bit, they use qubits. Like a simple computer, a traditional computer, they use binary and zero, but qubits, one is not one. One can be both one and zero. It's a little bit philosophical, but it is what it is. So the next slide. This one is entanglement. Entanglement in quantum physics says that two matters are quantum entangled. What is it? They say an atom have a pair that are quantum entangled even at an opposite point of time and opposite space. They are quantum entangled. If we can learn the state of an atom at one point, we can learn about the state of its pair at the other point of time and space, because we can just learn about one thing and we can know about the other pair immediately means that the computational complexity will be reduced and the speed will be increased. Because of that, the quantum computer can have an exponential improvement over the traditional computer. The next slide.
Okay, this is my part. Will quantum computers break encryption? Here I list down the two famous algorithm, which is Shaw algorithm and Grover algorithm. And from a research paper, we can conclude that Shaw algorithm was faster than Grover algorithm for computing integers factorization. This is a result from a research paper I get. I cite this where I can brief about the Shaw algorithm. It's a conceptual quantum computing optimized for soft for prime factorization. It takes a factor and output its factor and it use reducing number of steps to find a prime factor that can potentially cracking a public and private key. This algorithm is broken into two parts, which is a reduction of factoring problem to the problem of order finding, which can be also classical computing can be performed this, and the second part, a quantum algorithm to solve the order finding problem, which is this algorithm is a lack of capability. And we go to the Grover algorithm. Grover algorithm allow users to search through a unordered list for specific item and imagine we ordered unordered list of a certain number of elements as to find an element among them to specify system condition. We can use classical computer. However, quantum computing with a superposition to multiple the input simultaneous. So Grover algorithm can optimize to be faster to find the answer. And that's all. Next.
Okay, next we present why quantum computing require quantum cryptography. Okay, in the future, because quantum computing is still uh, development, we will sure predict that interacting the usage quantum mechanics will more directly with the coming of quantum computing and quantum internet. So quantum computing logic gate of quantum computer exists instead of quantum superposition, like my friend said just now. So what this does is that allow iteration of certain type of calculation to be done in parallel. So next time in the future, if we use this type of thing, we can like use we do two things in uh, parallel, like multitask. Like we can like and dislike at the same time. So next is a quantum computer. Now they can calculate prime factor of large number extremely quickly. This is not good for what we call because prime factoring in is the cornerstone of internet cryptography. If you want to use it in the future, so it's not good. So right now is for quantum computing. It's impractical if we use private key because it's hard to pass the private key nowadays. It's online because still is unsecure. So we use public key. And the most widespread use is like RSA protocol. So although this most appropriate use, statistics say that if we use like quantum computing to break this RSA protocol, we only take less than a day. It's that easy because it's still unsecure. But we still do because it's the most secure right now. So that leads us to next is quantum internet that is uh, most likely relate to quantum key distribution. Quantum key distribution lead to the Heisenberg uncertainty principle and quantum entanglement. The uncertainty principle tells that we cannot simultaneously know the value of certain pair of properties. And quantum entanglement, like my friend said, Khilfi said just now, it creates a pair of particular quantum property that is correlated between two. So internet today, because quantum is still moderately safe, you can say, although we don't use quantum computers. Because although we gonna use quantum computer in the future, it says that smarter classical security protocol also will be compromised because the advancement of technology nowadays. So then we need also to do that, to make it secure. We need to use the private key. So we need to use quantum cryptography and for like quantum internet to have a more secure encryption. So although quantum internet nowadays is still in, it is still in theory, and the researchers say it's still very hard to do much, although it's much in future. But quantum computing is used around, and most of it, uh, to have a more secure right now, we use like the theory of post-quantum cryptography. So that post-quantum cryptography, I'm gonna pass to my friend, Brother Faris.
Assalamualaikum warahmatullahi wabarakatuh. My name is Mohamat. I'm going to present you about post-quantum cryptography. Okay, what is post-quantum cryptography? Post-quantum, it can be described by substituting the vulnerable problem with problems that are very hard for quantum computers to solve. Okay, next. For the post-quantum cryptography, the candidate is next slide. Is lattice-based cryptography. Okay, let's say a two-dimensional lattice has a grid of a point that, and the problem is to find a point in the grid that is closest to the fit central point in the space known as the origin. It is very easy to solve by drawing the grid of the point and instantly obtain the answer that is the closest one with the origin. With hundreds to thousand dimensions of lattice might be hard to figure out or even to draw or imagine the possible point. More than that, evident that quantum can solve the problem is no. Next. Okay. Code-based cryptography is a public key crypto system with error correcting capability created by Robert McAleese. It uses linear error correcting codes to perform encryption and decryption by using different key to encrypt and decrypt. This system uses matrix multiplication with random permutation and non-singular matrix, as it's faster to encrypt data compared to RSA and less vulnerable from quantum computer attacks. To decrypt the cipher text, simply undo the error correcting of the process. Alright, the next cryptography is multivariate polynomial cryptography. Okay, multivariate based cryptography is solving system of nonlinear equations in finite field. Public key is a set of quadratic equations constructed from a mapping function. Private key is the mapping function used to construct a public key. Inverse mapping function will be the decryption function. Solving system of multivariate polynomial equation is proven to be the NP hard, which is non-deterministic polynomial time hardness. Okay, the lastly, hash-based signature. Quantum cryptography generate a random number for every possible signature known as hash. Signature are the random number. One of the important part of the hash base is the Merkle tree. By taking a very large key and compressing it down to a hash and producing a very large signature. In practice, the Merkle tree is used on and only generate a portion of the signature and compresses the public key to a single hash. In conclusion, the protocol of an existing encryption system to break by quantum computer might take 1,000 qubits of quantum computer, while IBM only had built one quantum computer with 65 bits. And also, quantum computer could take years to accomplish from 65 qubits to 1,000 qubits. It could say that we still have time to do some research to get the most efficient post-quantum cryptography. That's all for us. Thank you, Dr. Prof. Ahmad. Thank you for teaching us, and that's all for me.
Thank you.
Thank you.
Thank you, sir.
Thank you, Prof.
Yes, sir.